Hello everyone, welcome to the third talk in our lecture series. This talk will be given by Srigyan Nandi from B.Math third year. The topic is Introduction to Topological Groups. So, over to you.
So the last two lectures, in the last two talks, Rahul introduced some basic theory on the representation theory of finite groups. So in this talk, we will introduce the very object for which we seek to study those representations, right? So in a sense, the theory that we have built for these finite groups, they can extend to topological groups, because when we are dealing with topological groups, we have a notion of, in some sense of speaking, a kind of smallness by imposing conditions like compactness. So essentially, the theory that we develop, we could, like the theory of characters and Schur's lemma and all that, we could do these things because the group, in a sense, was small. And one, for the case of finite groups, it was by the very virtue of it being finite. But it would be apparent that things can be extended to groups that are small in other senses. And one of the most classical sense of defining small or smallness of a space is by giving it a topology and allowing it to be compact. So we are going to study how we can give a topology to these objects and then get some properties of these groups that allow us to, in fact, study their representations through vector space. So this talk won't be very heavy, and in fact I plan to finish it earlier than the stipulated time, because a lot of the things that we will be talking about, it is very familiar things like what a topology is and basic group theory. So we will start, as is right, with the definition. So it's a fairly obvious definition. We are going to see what a topological group is. So obviously it's a group and there's a topology. Topological group G is a group endowed with or on the same set we end up two different structures, one being algebraic and the other being topological. So the definition alone does not make sense, and in fact it is not yet a complete definition. These two structures that you have imposed on this set must interact in some way. Otherwise, we can just go around vaguely imposing different structures on different spaces and ultimately get nothing much really out of it. So when we do impose a topology on a space, one of the most natural questions are, what are the open sets, right? Because that will uniquely give my topology. Ultimately, my topology is a collection of open sets that satisfy those three properties of being open under arbitrary unions and so on. So here, we don't really want to do that. What is a next way of defining a topology? How do we define a topology without explicitly going into the details about giving all the open sets? And one of the ways we do that is, at the heart of it, topology is the study of continuity. So the first thing we do is we want to decide which maps that we want to be continuous. From that, we'll see if we can uniquely get a topology. So I have a group, right? I have a group. What are my most standard maps that I can think of on this group? Group multiplication. Any other map? Conjugation, yes. This is kind of close to conjugation. So forget any other additional structure. When we deal with the axioms of group theory, what are the two maps that we first see from the axioms itself? So one of them is multiplication, obviously. The fact that the group, yes, precisely, the inverse map. So we want these two maps to be continuous, right? So, such that. So I'll start with multiplication. So, but multiplication, it requires some construction. It's a map from G cross G, taking tuples of G, G comma H to the product G H. So I want that map to be continuous. So the map product E from G cross G to G that takes G comma H, the tuple, to GH is continuous. Note that this is not really well defined, because now we're considering a map between two spaces. One is G cross G and the other is G. So we need to define a topology on this. So the natural thing would be whatever topology this had, the product topology. So I will just highlight it. It is endowed with the product topology. Alright. And next, the simpler case, that is to ask for the inverse map to be continuous. So in G to G, taking G to its inverse, this must be a continuous map. And that is more or less it. We have a space, we have an algebraic structure given by the group, and we want to put a topology. We cannot give the explicit open sets. So we say from the algebraic structure there are some induced maps or natural maps on this space. We seek that those natural maps are continuous. And any topology that allows for these natural maps to be continuous, that's a topological group. That induces, that gives this structure a topological group structure. So let's just reformulate these things. Okay, right? So let's just reformulate these things. So instead of just taking continuity, we'll use the definition of continuity, that if F is a continuous map, then F inverse every open set is again an open set. So what does this say? This says that since the product map is continuous, let G belong to G, let G lie in G, and let U be an open neighborhood of G, and let G equal to some G1 times G2, right? So under the product map I have that G1 comma G2 is taken to G. So if U is an open neighborhood of G, that means I have two neighborhoods. There exist open V1 and V2. In G, such that G1 belongs to V1, G2 belongs to V2, and what is the third condition that has to be satisfied? It has to be an inclusion, obviously. So what would that inclusion look like here? It's a continuous map, right? So obviously the pre-images, I have given an open set in which the pre-image will be contained. I must have that the image of this open set that contains the pre-image that lies inside this open set that I took in the domain. So what is the image of this total open set? It is going to be the product V1 V2 should be contained inside V1. V1 V2 is precisely the set containing the individual products of elements from V1 and V2. So similarly, what does 2 state? So 2 states that the inverse map is continuous. So basically any open set that I take here, say U, so or any open U G, the set U inverse equal to such that U belong to U is open in G. So we define the topology from requiring the continuity of 2 maps, but automatically, due to the inherent group structure, this already gave us a lot of information about what open sets look like. Given an open set, how can we get some more open sets? One of them was taking U and taking its inverse. Another said that given a U and given an element G inside U, such that G is the product of G1 and G2, there exist 2 new open sets that contain G1 and G2 individually, whose product within themselves is again contained in G, right? So this is just a restatement, and even though it's a trivial restatement, because this is basically what I've written here is word for word 1 and 2, it has given us a lot more information about, in a sense, it will shed some light about what the open sets may look like in this. Although this is far from perfect because there is still so much about the open sets that we have no idea, right? So before getting into any examples, you would have already had some examples in your head because a lot of standard sets that you know, such as R, when they are used with a topology on which you can do some operations like addition or multiplication, they are already topological groups, and it requires nothing to verify those things. So you cannot go about giving any group a topology and call it a topological group, of course. These two operations have to be satisfied. So let's start with a non-example, right? You just do one. So and one of them would be to take the space, let's take the group Z2 and plus, right? It's an additive abelian group. It has two elements, 0 and 1. So I can define my open sets. So I'll write this tau for the topology. And I'll say the topology in this, it is precisely these sets. One is of course the null set. I can take, the topology by definition must contain the whole space. So phi and the whole space obviously. And I'll say the singleton 0, right? Verify that this is indeed a topology, right? So now, is this a topological group? Does anyone can anyone give a reason why this will not be a topological group? It's a very basic group, no complicated machinery going on.
Zero is okay, but so the prime is 1 plus 1.
That's right.
Yes.
So zero's pre-image under, that is the product, because plus is the product here. Zero's pre-image is the set 1, 1, 0, 0. This is obviously not open in the product topology since it's a finite topology, so the product topology's open sets will precisely be the individual Cartesian products. So yeah, this is a non-example. So there are so many topologies and so many group structures that you can give on very familiar sets, but they will not induce a topological group structure. And there is a reason why this structure is so special. And we'll see that later, although there are lots of reasons. We'll actually see that this structure induces it allows for some very strong results, especially with the separation axioms and when we come to study the isomorphisms and homomorphisms between these objects. So now we'll go through a small routine procedure of giving examples. So let's forget any familiar space. Let's take an arbitrary group G. Right? Can you give me one topology that makes it a topological group?
The discrete topology.
Exactly. Every map is continuous in the discrete group. You have nothing to worry about. And just as a reminder, the more open sets you have in your domain, the less likely your map is to be continuous. As in, the finer your domain is, the farther away in a sense it goes away from being continuous, and the more coarser the finer your range is, the farther away it is from being continuous, and the coarser your domain is, the less likely it is going to be continuous. Because you ultimately want more and more open sets in your domain to catch those inverses when they come back. So yeah, that is one. Again, I would ask the same thing. G being a group, can you give any other standard topology that makes G continuous?
So trivial topology also works.
Trivial as in the indiscrete.
Yeah.
That's correct. So that being the open sets are precisely G and the null set.
G and empty.
Yeah. So I want to state that as a second example. Discrete, trivial. Alright, so standard examples doesn't really give much information because these are just the examples pulled directly from the definition. No, it doesn't give any insight as to what is actually going on here or what the machinery is. So, what else? Now, can you give me some standard spaces that you are familiar with, that have group actions and whose topology you are familiar with? R plus. And no need to verify, it's a real analysis result that addition is continuous. I mean, addition acts nicely. Again, R star, that is the non-zero reals, multiplication. Same for complex. And singular. For those looking for an exotic example in these lines itself, you can obviously go consider things like quaternions and whatever. Doesn't matter. Same topology for quaternions, because you are essentially extending the Euclidean topology for quaternions was R4. Right?
R4.
Yeah, R4. So fine. Now let's see. Any other exotic example of a topological group? It's a very important example in the sense that we will be revisiting it a lot of times. So a lot of places denote the circle by T, but yeah, that's one. So what is the operation here? What is the group structure in this?
We treat it as like the complex numbers of modulus 1.
Exactly. So it is multiplication. Everything will remain within the circle. And again, since it is complex multiplication, it respects the topology, right? That's good. So in fact, this example that Sarvesh gave should motivate one of the next things, because this is not going to be a very interesting talk. It's just a revision of group theory and topology all over again. We define concepts, we see where how to create new concepts from old. And that's essentially what is done in a group theory 1 course or a topology course. So Sarvesh gave a subspace of C, right? And that had its own structure of a topological group. Can we extend this to arbitrary topological groups? What subspaces of topological groups will themselves be topological groups? Is there something?
Compact subspaces.
Those which are closed under multiplication.
Yes. Those are subgroups themselves with the subspace topology. Subgroups with subspace topology. Right? We have come to one of our main things. We had an idea, we could now create that same concept from old concepts. And we did it by going through the subspace. Right? So now a lot of these groups that we dealt with, they are in fact metrizable. All of these are metrizable. So is this, right? So we can equivalently go on and give the epsilon delta definition. So a topological group, a metrizable topological group, that is a topological group with a metrizable topology for which a metric exists. That is a group with that metric structure such that epsilon delta for this, epsilon delta for this. I won't, it's too long to say that epsilon delta thing, but you get the idea, right? Because epsilon delta is equal to continuity. So now that you have epsilon delta here, let us go and find some, although not non-trivial, but a bit further away from these bland everyday examples, right? And a lot of these groups have come, we have come across, and especially so in the first two talks of this semester's math club. So that is GLNC, GLNF. Why are these topological groups? Again, the reason is, not the reason, but I did mention that epsilon delta holds in case it is metrizable. And we know the topology that we give these. We have a n cross n matrix, we just slice it up, stretch it all out, give it the Euclidean R n cross n topology, right? So, why are these topological groups? Because now when you do matrix multiplication, it's a very routine and bland process to check, but ultimately your entries are polynomials of these two things. Polynomials are continuous, so it doesn't really matter. So that's trivial. Product is continuous operation. Inverse, not too special, but again the determinant is a polynomial operation. And once you have the determinant, it's a quick application of whatever. You can do it in so many ways. Kramer's rule, adjoint, or whatever. So the inverse is continuous, and the product is continuous.
Finite groups are what dependent that discrete groups have also the graph metric topology as they are criteria.
So you are putting the graph metric on the group G.
Yeah, for any finite.
The word length metric, right?
No, not the word length metric. As the graph metric in terms of group, every group has the daily graph.
Yes.
So the graph metric of that daily.
What is a graph metric?
Like
Okay, let's start with that. I don't think that is it. So, okay, let's just see. For Z3, what does the KD graph look like?
for that three.
Yeah.
Three edges.
3 edges.
Three edges.
That will not induce a topological group. So, for Z3, the problem is we are going to have Z3 is empty. So, 0 plus 1, 0, 0 plus 1, 1. Plus 2, 0, 0 plus 0 is 0. Okay, I'm not too sure now, but I don't think that will necessarily induce a topological group. Because I am immediately I'm not seeing how it will have the topology naturally has anything to do with the product and inverse. I think okay, we'll try that out later. I still think
if you overcome the like the genetics expert inverse, I think will be tricky.
no, even the product comes under the generating sets.
So edge search deployment might generators. I think for inverse it will be tricky.
This metric takes integer values, right? So
Yeah.
in that case, okay. Now I'm actually not too sure whether that will work because since it's discrete and the metric takes integer values, it might work. So even for product, I don't see how that has a natural this thing naturally imposes a continuity with the product. Okay, we'll come back to that and try it out. So yeah, we have that GLNR and GLNC are topological groups. So now, as I said, we'll try to further shed some light on what the open sets might look like, or from one open set, how do we get more open sets, or for that matter, closed sets. So some of the later theorems I won't even bother to give proofs because the maps that you require are fairly natural and it's just a routine verification of continuity arguments or isomorphism. So one of the first things that you can notice is that if G is a topological group, then what maps do we have from G to G? We have the left translation, right? Fix let G belong to G, and we have LG from G to G. H goes to G, right? So what can you say about this map? This is you will start to see how these two axioms for the continuity of these two maps, the product and the inverse, how powerful they are, because it gives a very neat characterization, although not complete, but a very neat characterization of open sets that we could use, and a lot of properties that open sets share among themselves, sort of closed sets. So, by the very definition of a group, this is an isomorphism, right? It is bijective. More than that, if I take gamma to G cross G, if I define this map gamma G from G to G cross G, which takes H to H comma G, right? This is basically, if we take G, it is identifying it with one line in this, that is isomorphically. This is injective and continuous map, obviously. So this is continuous, and so what happens here LG is nothing but the product of gamma G. Two continuous maps, and we took their composition. So LG is in fact a continuous map. It is a continuous map, and what is the inverse of LG? That's LG inverse, obviously. And so we defined LG to be continuous for any element G. So this is a very powerful map. It is an isomorphism, it is also a homomorphism. So that allows us to come to some very nice conclusions. So I don't want to use the nomenclature yet, but we'll just get on with it. So what we call maps like LG, we call them topological isomorphisms. LG is homomorphism and isomorphism compatible. Alright? So LG is a topological isomorphism. So similarly, RG, the right translation, these are translations, that is also topological same, right? So when we have homeomorphisms and we are trying to shed some light on these nature of these open sets, these homeomorphisms are very important, because when you do have an open set, the action of the homeomorphism on the open set is again an open set. So a lot of new open sets can be generated from these very open sets that we have. And this is extremely powerful, because what are we doing now? Let V be open in G, then any coset, so as to speak, of V is open in G. It's a completely new set, because V is not equal to GB unless G is identity, because these are injective actions on groups. Then GB and VG are open. Not only that, since it was a homomorphism, the converse holds. So if any GB or VG is open, then V must be open in G. So V is open in G. In fact, this is also too good a way of writing it. Then GB is open in G, which also has a both way implication that VG is open in G. Okay. So this is very nice, because from one open set we have that all its translates going right and going left. These are all open sets, and these are not things like subsets that are open. These are completely new sets that are open within themselves. So this is very powerful, because a lot of times when we try to get new open sets from old ones, we seek some kind of relation, and from a topological point of view, it is almost always, it deals with a set theoretic connection between the two, and that lies in the domain of some sort of intersection, or one being containment, basically. So here we can develop completely new open sets that are pushed and motivated by the algebraic operation for this, right? So we have that translates our homomorphism. So similarly, inv is a topological isomorphism. Right? So, oh, by the way, just the fact that it is an isomorphism and it is continuous in one way does not imply that it is a topological isomorphism, right? You can have a lot of isomorphisms that are continuous in one way, and although their inverse exists as an isomorphism, the inverse need not be continuous. So that condition is really necessary. So inv particularly is a topological isomorphism. Inv was obviously continuous as what we got from the definition, but obviously inv of inv is equal to identity. So inv's inverse is identity. So inv also satisfies the same properties, and it is a topological isomorphism. So initially, just from the continuity of inv, we had that if V is continuous, then V inverse has to be continuous, right? But since it is a topological isomorphism, we have a much stronger thing. V open is equivalent to V inverse bingo. So these two are the same things. So left right translates and under inverses, since these are in fact topological isomorphisms, they again give a lot of ways to obtain. And then there are so many things you could do. You could do conjugation and whatnot and get more relation. But for the two special results that I want to prove, these actually suffice, and in fact these are more than enough. So so there is one characteristic property of open sets that contain the identity, and I have to make note here that the identity will play a very important role in this in the study of topological groups. A lot of questions on topological groups can be boiled down to questions of what happens on the identity, because in a lot of ways the identity is similar to every group. It can be pushed around here and there to the group, and it comes back and brings a lot of properties back to it, and it also sends a lot of properties around the group. So I'll start with a property of an open set that contains the identity. It is a characteristic property that we will use in a lot of the coming proofs. So it's a very nice property because in a sense it compactifies and combines the essence of the two axioms for topological groups that we needed. So let's see. Let U be open in G and let U contain the identity, right? So let U be open in G and let U contain the identity. There exists an open subset, there exists an open V in G such that V also contains the identity. More than that, V is equal to its inverse and V dot V is equal to V dot V is contained in V. So we have captured the essence of the inverse map, we have captured the essence of the product map. And this is a very important characteristic property. So the proof is again not too hard, but I will just sketch it. So E lies inside this U, right? So and we know that under the product of E comma E is equal to E, obviously. So therefore there are two sets, V1, two open sets, that is V1 and V2 that both contain E. So I shouldn't write like this because they should have an intersection. So I can draw a V1 and a V2 that contain E, right? So now since both V1 and V2 contain E, V1 inverse will also contain E. So we have V1 inverse here and we have V2 inverse that contains E. Right? So all these sets contain E. So we will do the most natural thing and we will define V to be V1 intersection V2 intersection V1 inverse intersection V2 inverse. Finite intersection. So it's closed. This still remains an open set, and of course this is non-empty since all of these sets contain. This is precisely the set that we want because it consists of intersections of open sets with their own inverses. So it will trivially satisfy V equal to V inverse. And since we have V1 and V2 here, and we had by definition that this V1 here, that this V1 dot V2 was supposed to be contained in U, and V lies inside V1 and V2 because it is the intersection. So we also have V dot V is contained in U. So this it might not seem powerful, although it should because it combines two important properties. But we'll see how to use this result later. And one of the first surprising results that we'll come across is a very natural consideration or a very natural question that we will ask for our space. And that question deals with one of the separation axioms. So essentially, right, because from analytic point of view, we are almost never interested in non-Hausdorff cases. So this is naturally that we have built up and got sufficient information about our open set. We'd like to know when this nice property is satisfied, right? And now it turns out that obviously in standard topological spaces, Hausdorffness implies that every single point set is closed, right? So Hausdorffness implies the T1 axiom. But for these topological groups, we have T1 is equivalent to Hausdorffness. And more specifically, what we do have is that you don't even need all one-point sets to be closed. You just need the set containing identity. That singleton is closed. A very powerful result in group theory, which will actually allow us to start thinking about building another very natural thing, which is quotient spaces, since we have an idea of quotients from groups and quotients from topological spaces. So again, as in most cases, I will not give the full proof. So, of course, G Hausdorff, that will automatically imply that G is T1, which will imply that E is closed.
Can you recall what is T1?
T1 is the first separation axiom that says that every one-point set is closed.
Okay.
So Hausdorffness implies T1, but it is not necessary that the case is that T1 implies Hausdorff.
Yeah.
A lot of T1 spaces that are not Hausdorff. Actually, should give an example.
No, that's okay. I'm
It will be some finite set topology, something, some weird. Is finite complement topology T1? It's not Hausdorff. I don't think it's T1 either. Something. Just try. I clearly remember one counterexample was a topology with 3 elements in it. So we find it so yeah. Okay. So alright. So we have that. So now for the converse, that is to just start with this humble assumption that E is closed, we will go on to prove that G is in fact Hausdorff. So let E be closed, right? So E is closed. You can already see E is closed implies T1. Why? Because right action by G was homeomorphism, a topological isomorphism. So what is the right action? So homeomorphisms will map closed sets to closed sets. If this is closed, G of this will be closed, which implies G is closed for all G, right? So T1, we already have T1, so it was not that big a thing to build that T1, right? So now that we have that this is closed, we will in fact first show that G can be separated from any, the identity can be separated from any non-identity element. So what we do is separated, that is to say, there are disjoint open sets that contain each other. So now, since G is closed, so let G be this point and let E be this point. So since this set is closed, there exists an open set containing E that does not contain G, right? Let that open set be U. So we are guaranteed the existence of that open set. So now we will use that characteristic property, right? So there exists open V such that V is in fact contained in U. V is equal to V inverse and V dot V is contained in U and E belongs to V, right? So we have that, and now, so we had this open set here. How can I create a set that contains G? Because I need a separation, that is. So I can just consider G, right? GB is a translate of B, and we discussed that translates of open sets are themselves open. Now if I prove that GB and B are disjoint, I am done. But GB and B are obviously disjoint because left action is injection. So G can be separated from any element identity. So I won't give the full proof, but again it is a very trivial thing. So if I have any arbitrary G1 not equal to G2, what I will do is I will consider the element G1 inverse G2 and identity, and show that these two can be separated. That will in fact imply that the G1 and G2 can be separated. In fact, I can take simple thing to do would be to take U containing identity and V containing G1 inverse G2, and then all we have to do is show that GU and GB are disjoint, because now GU will contain G because U contains the identity, and GB will contain G1 inverse G2, which is G2. I show that these are disjoint. So, of course, two disjoint sets when acted upon by G will be disjoint. Then that follows from the injectivity of G. So that is one of the first strong theorems that we encountered.
I had a comment for you. So if G is a finite group, capital G is a finite group, and it has the Hausdorff topology, then it has to be the discrete topology, right? By the logic you've written, because E is closed. That means every singleton G is closed, but it's a finite group. So then literally everything, all unions are literally closed. Right?
How are all unions? Yes, all unions are closed.
Because
and
that
yes. So for the yes. The only Hausdorff topologies on finite groups are the discrete topology. Yes. So and that is one of the reasons why most people don't. They're not really interested in these topologies on discrete groups. And in fact, in many cases, when we see topological groups, we think, oh, okay, we're going to give these topologies on things that we learned like Sn and Bn and all. And it turns out not really interesting. And in reality, what we study is the brand normal groups like R plus, R with multiplication, all those infinite groups where it actually matters. Okay.
No, but for example, a metrizable group is Hausdorff, right? So if you were checking that, for example, this graph metric is metrizable, then all we have to do is check is that E is closed.
Yeah, and in fact, this so we have to see whether the graph metric gives the discrete topology.
Yeah.
Okay.
Correct. You have to check.
It does, because the distance is at least 1. So if
Yeah.
you take the ball with radius half, then that singleton itself is open. Assuming
That
that
will be every singleton is open, and hence yeah. Okay.
Yeah, those are that at least for finite groups.
Yeah. Okay, yeah, that is nice. And when you originally asked this also, I was thinking even word length metric will have the same thing, right? Because word length metric will give actually any discrete metric on this thing.
Anything will be.
Any discrete metric will make it a topological group, and it will make it the only possible Hausdorff topology. Nice. Alright. So, yeah. So now that we have this notion of Hausdorffness, we go to the next most naturally possible construction, and that is those of quotients, right? So we have quotients from an algebraic point of view, we have quotients from a topological point of view. So it is quite natural to ask this question. So although a lot of us may not be familiar with what the quotient topology is, so let's go through that. So let X be a space right? What do I seek to do in my quotient topology? As in a lot of algebraic cases with rings or groups, I seek to kill some relations, or rather, I seek to identify two different elements as one, and that is achieved in a sense by killing elements of a certain form. So basically, in an abelian group, if I want to identify A and B, I will say that A minus B has to go to 0, right? Because I want them to be the same. That is quotienting it out by the relation A minus B. So in a topological space, you are allowed to do the same thing. But here, we do not have any algebraic motivation for it. But it is purely what you would expect it to be, gluing. You want to identify two things as one, so you are gluing it. So you take a napkin and you want to glue two of the points as one. Let us just say for the sake of simplicity, it is the two end points of the corner. So you get some weird, I don't know how to describe that space, but you get something, right, by gluing those 2 points. So that can, in fact, that new space that you get, it has a unique topology, and that is the quotient topology of this gluing map. And just the way we defined our topology by the continuity of two standard maps, that is also defined by the continuity on more precisely, it is a lot of topologies can make their quotient map continuous. More precisely, it is the final topology, the finest topology that makes that gluing map continuous. So let's see. So how do I start off when I want to glue some spaces? I have to select which set of points will be glued to each other, right? I can partition my space in that way. Points that will not be glued to anything, they will be kept in a separate class in which they are the sole residents, right? And let's say on my napkin I wanted 5 points to be glued together, 5 points which are colored blue, and maybe 2 points which are colored red, and those I want to be glued. So those 5 will be kept in one class called the blue class maybe, and then the remaining 2 will be kept in the red class. And maybe I can say I didn't want any of the remaining points to be glued. So each of those remaining points will be the sole residents of that class, right? So this is a partition. The next thing that should come to your mind is it's an equivalence relation, since it's a partition. So the way to start is let B and right? So I can define a natural quotient map. So what will my quotient topology look like? It will contain all the points that I wanted to be identified will be the same point. So it will look like the classes, the partitions of this basically. So my quotient space is actually going to be X by this, the set of all partitions. But what topology do I give it? I will give it, so obviously I will mention that we'll have to take the quotient map towards this, that is Q taking X to X by this thing. What is this map? The quotient map, it maps every element to the class in which it lies, right? I want this to have a final topology with respect to this. Although the actual way we define it will not have anything to, it will have a lot to do with the notion of a final topology, but I will not go ahead and prove why it is a final topology. So basically, I want to say what the topology of this is. So I have to declare what the open sets are, right? So my definition for the open set is U is open in X by if and only if, Q inverse U is open in X, right? So this is what we have, and you can easily verify that this topology in fact does the most rudimentary things first. It gets rid of those, and that is, it ensures that this map is in fact continuous. And then the if and only if condition, that is U is open if Q inverse U is open, that ensures, because we have that if U is open, then Q inverse U should be open. But Q inverse U being open, implying U open, is not a continuity condition, and it is often called strong continuity. And that actually gives you the notion of the fact that this is in fact a final topology for this map. Right? And final topologies are very important because a lot of topologies on function spaces and so on, they are not defined by explicitly going through the baby steps of giving the open sets and all that. Ultimately, topology is studying continuity. It will take a continuous map and it will try to give the finest or the coarsest topology on these maps. Right? So we have this, and now it is unfortunate that quotient topology forgets a lot of information of the space itself. And one of the most important pieces of information that it tends to forget is that the space was Hausdorff to start with. So, just to get into this, can you give me a Hausdorff space whose quotient topology, whose quotient space is not Hausdorff? Simple. Anything that was Hausdorff, a very nice space, but when glued with some of its own points, it didn't. It doesn't yield another Hausdorff space. So.
In your quotient space, if there are two points, I mean, in your space there are 2 points that are glued in your quotient space, so you cannot you cannot find 2 open sets which separate them.
Yes, but that is the definition.
Yeah, that's why.
No. I am not saying the quotient topology is not Hausdorff. In many cases, the quotient topology is Hausdorff. The very napkin example that I took, if you glue these 2 endpoints, it is still a Hausdorff space.
How? Those 2 points are the same, so you
Right.
can.
But there are topologies that are Hausdorff, but their quotients, when taken in a certain way, might not result in a Hausdorff topology. So, okay. So one way to see it would be take a circle, right? Take a circle and start with a point, right? Now rotate with an angle, with a fixed angle theta. But in this case, I will rotate with an irrational angle. Alright? I will not rotate with a rational angle. Will always come back. I will rotate this with an irrational angle, and hopefully, but okay, even though the proof is not necessary, do you intuitively see that when I rotate with an irrational angle, I will never come back to any of my points? And in fact, it will go much farther than that. The set of points that I'll finally get on my circle will be a dense subset of this circle, right? If I quotient those, I will no longer get a Hausdorff topology, even though the circle I started with was Hausdorff, right? Because points outside this, every neighborhood intersected some point which was in a gluing class. So ultimately, my quotient topology will not be Hausdorff. And these are a wide, this is a very important class of examples in algebraic topology that generate non-Hausdorff spaces from Hausdorff spaces. And it comes under a set of, it's a special case of a set of transformations known as Dane twists on cylinders. So, anyway, that is outside.
We can also consider the RK topology and consider the set K to be like that is also an
Yes,
example.
that's correct. In fact, I think that is one of the examples you did in the summer.
Yeah.
So, could you say it again?
So we consider the RK topology and we collapse the set K to a point.
K is 1 by m.
Yeah. Set of points of point.
This is a identifying. For those who don't know what the RK topology is, nothing to worry about. But for those who know, this is in fact, it does generate a non-Hausdorff topology. So a lot of interesting examples. So there is, we can take 2 real lines, right? And we can collapse every 2 points within themselves, except these 2 origins, of course, right? So these 2 origins are kept separate, but if the one here goes to the one here, one dash here, okay, whatever. So this actually gives a very weird space. It is this 2 points here and like this, right? This and the topology is, it is called the line with 2 origins, right? This is not a Hausdorff topology. Every open set containing this must contain these 2 points, these 2 origins you will not be able to separate. And this is again a very interesting generating class of examples in ASTO. So you can take the line with n origins and quotient randomly here and there, keeping weird points out here and there. So yeah. So one standard thing to note that I will say an equivalence relation. I will say this equivalence relation is closed in X if all partitions of this relation are closed. Closed subsets. And you can see that if this equivalence relation is not closed and X is Hausdorff, then X by this equivalence relation will not be closed. Because since the equivalence relation is not closed, there exists a partition that is that contains a limit point not lying in itself. So that limit points, every open neighborhood will intersect something in this partition, and that will not allow the quotient topology to be closed. So yeah. So now we go into the actual important thing. Should be done in another 15 minutes. 4. 20. Yeah. So now we have the standard quotient map from X to X by this. So from the definition of the quotient topology, we have that Q. A very important property that we seek is that Q being an open map, because quotient maps, you have a lot of quotient maps, and quotient maps a lot of quotient maps tend to be open maps or closed maps for that matter. So Q is an open map. An open map between two topological spaces basically takes open sets to open sets. So Q is an open map, and the condition for that can be gotten from the definition. That is, U is open in X by equivalence if and only if Q inverse U is open. And that will basically say that if Q inverse of Q of U is open in X. Because Q is an open map if QU is open. But that is the same thing as if and only if Q inverse QU is open. And that is a criterion that we wanted. So now, we have this, and we have a very short proposition. So when do we have these open quotient maps? So let G and let H be a subgroup of G. So when is this quotient map from G to G by H open? So Q G to G by H is open. The quotient map will be open. Oh, by the way, I did not, I just took H to be any subset. It was wrong to say this. Right? Q from G to G by H is open if H is in fact a subgroup of G. I am not saying it has to be normal. So when I say G by H, I mean a topological quotient. Right? So if G by H here will actually just be the cosets of G. So this is open if H is a subgroup of G, and that is very easy because the condition that we required was Q inverse of QU has to be open for every open U, but Q inverse of, where are the chalks? Yeah. So Q inverse of QU over here will be equal to the product of U and H, right? But that is basically nothing but it's basically the union as H lies in H of HU. But what are these? These are individual translates of the open set. So this is also open, and that only happens if H is a subgroup. Because if H is a subgroup, we have this relation that Q inverse Q is in fact those quotients of elements of U by H. So now these next two propositions I will not give a proof for, but the proof idea mostly follows this. So we are not going to introduce any new method. It just uses the fact that the characteristic for open sets of G that contain E, right? So of course, since we introduced Hausdorffness, we won't randomly go around quotienting groups here and there, because we want our quotients also to be Hausdorff, and we are essentially building up to that. So let G be a topological group and H be a closed subgroup. Right? So here we have a closed equivalence relation, and therefore H here, then G by H is Hausdorff. So we have a nice characterization of a family of H that we can take when we want to quotient, we obtain a Hausdorff topology. And of course, the result here will rely on the fact that since H is a subgroup, it induces an open quotient. So,
What is an example of a subgroup that is not closed?
Subgroup that is not closed. So let's see.
Like Rn and GLNR.
Rn is not Rn square, that is. You are taking Rn square, right? And then GLNR.
Rn with addition. GLNR.
Rn square. Because GLNR is Rn square.
Oh, sorry, yeah.
Oh, yeah, fine. Then,
Sorry.
and we take GLNR.
GLNR is open, it's not closed.
Yes, GLNR is, yeah. So the problem is invertible matrices are dense in the space of this thing, right?
Wait, this GLNR is a group under multiplication.
Yeah.
Because that's
But
what-
Rn is not a group under multiplication.
Okay, then that's.
Subgroup that is not closed. So obviously we cannot consider discrete groups.
Yeah, discrete groups are not. That's why.
I think in GLNR, if we take I remember SUN or either SLN, one of those. Okay, you have to verify this for yourself, but SLNC is actually dense in GLNR, I think. Either one of SUNC or SLNC. So the special unitary group or the special union. No, it was SUNC. Yeah, it is SUNC. So that is actually dense in GLNR. So it will not be closed in GLNR. So we have that.
Or we can take S1 and all the nth roots of unity for some n.
Yeah, that is also all the nth roots of unity.
Like the set of all nth roots of unity for any n.
That is closed. It's a discrete set.
No, for any n. Like,
Oh,
like,
for
so
all.
the second
All
one
yes,
is all
yes.
n.
All
Yeah, that will also be another dense thing. Yeah, in fact, SUNC is also a dense thing. Even that is a. I think that is a generalization in higher dimensions to
N equal to 1.
Yes, that is the thing. Because SU1C is obviously the circle. So, fine. So, yeah. So, finally, we would like group structure. So far, mind you, we have not yet given a group structure on G by H, right? So this will finally culminate to this theorem. And when is G by H a group? H has to be a normal subgroup. So let G be a topological group. Let H be a closed normal group. Obviously, in both these cases, I assume that G is Hausdorff. Then the quotient, finally, we could develop a quotient that is also a topological group. So G by H is Hausdorff. Topological. So this just goes to show that in spite of the tools that we had readily available in front of us, because of these two strong conditions that we imposed in the beginning, we could just not go around and quotient by anything, because at the end of the day we seek more useful spaces from useful spaces. We cannot just go and do whatever we want to get arbitrary spaces. So we come to the last section in this topic, and which I have already discussed in part at least for the definition. And that is the notion of a topological homomorphism and a topological isomorphism. Topological homomorphism is a group homomorphism that is also continuous as a map between the two topological spaces. I don't think I need to write the definition. And the topological isomorphism is an isomorphism that is continuous and whose inverse is also continuous. And both things have to be verified, because since the group and the topological structure were separate in many cases, or at least to say more often than not, you end up finding maps that are not too well behaved in this sense. So, yeah, so let us actually see something that is a direct counterexample to what I just said here, right? So, let G equal to K equal to R plus, right? Both of these are the same set, they are the same group, but so I want a continuous map, but a reverse map that is not continuous. So I can say let G have discrete topology, let K have Euclidean topology. Right? So what is a very natural map that I can give from G to K? That is the identification. They have the same underlying set on which they build their algebraic and topological structures. But is this identification? Yes, it is an isomorphism of groups, obviously. But is this identification continuous? Yes, it is continuous, because G has a discrete. Oh, okay, my bad. I should say which sets I am taking, where to where. Identifying G to K, right? That is my bad. So G, since it has the discrete topology, every set is open. So every inverse, when you pull it back to G, it will be open. So this is continuous. But is the inverse continuous? Although it's an isomorphism, the inverse need not be continuous, because when you are going from K to G, just consider the open set 0 in G. Its inverse will be 0, but 0 is a closed set in K. And sorry, that's wrong. 0 is a singleton in K, but K has the standard Euclidean topology. Singletons are not open. So again, it emphasizes the fact that it is very important that the continuity goes both ways. So again, one standard thing for any G, the map phi h from G to G, given by, you can guess it, conjugation. G going to, this is a topological isomorphism, and that is very easy to see, because what are we doing? We are doing a left translate and a right translate, both of which are homeomorphism. And trivially the inverse is what? Again, it is from H inverse GH, it will be H G H inverse, which is again left right translate. So conjugation is a rich source of examples for this thing. Right. So now from this previous thing that we had, if K is Hausdorff. Oh, okay. I think my G was supposed to be Hausdorff here. No, first. If K is Hausdorff and phi G to K is, I will say phi G to K is surjective. I already know that kernel of phi, that is equal to phi inverse the identity. That is, first of all, it is obviously closed, since identity is closed, since it is Hausdorff, and it is normal because that is the property of the kernel, and it is a subgroup. So kernel of phi is a closed normal subgroup of G, right? And from okay, let's just keep that, because you might think now, does the first isomorphism theorem hold? Because now we just don't have isomorphism, we have topological isomorphism, and the sad thing is the isomorphism theorems no longer hold because of the continuity that we have. Not in general, the last few propositions that will come to, they will give, in a sense, the kind of isomorphisms that you can hold. So, and in fact, we immediately start with that. So, if phi is a group homomorphism and that is also continuous, then wait, do I want to do that? I think I skipped a bit ahead. No, let's do that. Yeah, alright. So this, I mentioned that we will encounter two special results, and one was the one dealt with the Hausdorffness of our space. So now this one is a bit surprising. So let phi from V to K be they require continuity. Be a group homomorphism. So I want the criteria that will tell that when my homomorphisms are in fact continuous, because we know the group structure very well. With the topology we don't know too well. So it is natural to realize that it is easier to say when the thing is a homomorphism than it is continuous. So the surprising thing here is that if pi is a group homomorphism, pi is also continuous. That is the same thing as pi is at the identity. If this one homomorphism is just continuous at the identity, it is continuous as a whole homomorphism of topological groups. So obviously continuity will imply continuity at the local point. So what we seek to prove is that continuity at this point implies continuity everywhere. So I think I'm running out of time, but the proof isn't too long. So it again builds on the ideas that we have used, and that is the characteristic property of, as you may guess, the open set that contains the identity. So when I say continuity at identity, I mean that for any open set that contains identity, the inverse of that open set is actually an open set in G itself. So this is another very strong result. So continuity has been reduced to a very local property. As I said, the identity travels around the group and spreads its properties everywhere else. And that is the special thing about topological groups. A lot of information topologically is abstracted from the topological data at the identity. So a lot of global information translates to just questions about what happens to the space at the identity. So I won't give the proof. we have two final things. So yeah, so if pi from G to K is a topological homomorphism, then what actually happens is that we can consider H to be kernel of pi, and we actually have that this natural quotient P, let's say, I shouldn't have used pi here, P from G by H to K. This is in fact, I am assuming that K is Hausdorff over here. This is in fact homomorphism. A topological homomorphism. So it took a lot of constructions to get these things, because when we just deal with group homomorphisms, it's a very algebraic motivation. But here we have to take care that our maps are also continuous. So that actually builds on from this, because all you will have to do is you will have to show that this identification, it is continuous only at the identity, and once you show that, you have that the identification was continuous as a whole to begin with. So
I had a question.
Yeah.
So if image of P is closed, then G by H to image K will be a topological isomorphism.
yes, and that is precisely the next theorem. So if H is kernel of pi, and no, I'm sorry, that will not happen. You will actually require that the map that you begin with, it is in fact an open map. Yeah, that proof is a bit long, but it is not that simple, because when we are dealing with the isomorphism, for the inverse to be continuous, we will have required that this is an open map. Again, a very long theorem, but yeah, I won't state it. So that's it. If this happens, and it is subjective, of course, and as he said, the same hypothesis, but we have the additional hypothesis that pi has to be an open map to ensure that we have a continuous inverse. Then we do in fact have that we have the first isomorphism theorem for topological groups. So finally, I'll just end with an example. And it's a very trivial example, and that example will be based on what he said. So you can consider this from R plus to the circle group S1, and that is the standard map. So what is the standard map from R plus to the circle group? The exponentiation. So P will go to e power 2 pi I t. So this is in fact a topological homomorphism, right? So nothing special to verify here. This is a standard map between two metric spaces, and we know that exponentiation is continuous. But more than that, exponentiation is an open map. And you can verify that because every open arc that you have here on the circle, it will get translated to another. Sorry, every open segment here will go into an open arc over here. So pi is also an open map. So from what we have from these lemmas, we will also have that there exists a continuous inverse. Even though the quotient is continuous, we require that the continuous, we require a continuous inverse from this quotient space to the image. So because of the because of the fact that this map is open, we have that the standard. Oh, what is the kernel of this map, by the way? Yeah. So phi is equal to z. So we have from the first isomorphism theorem that pi from R by z as a quotient topological space to S1 is topological isomorphism. So this we anyway know for groups, but this is very special in the sense that this holds both topologically and algebraically, and it's one in a series of very famous examples that in which the isomorphism theorems, the canonical identification of spaces actually hold both topologically and algebraically to give rise to topological isomorphism. So that is it. Do you have any questions?
So, any further questions? Any references?
So the reference that we are using currently is, I think, Vern Paulson's expository paper. What was the name? Representations of topology, Introduction to Representation Theory and Topological Groups. So it's the reference that is going to be used for all the 7 talks. And we also have, I think, G.B. Folland's abstract harmonic analysis.
So, in case there are no further questions, thank you for the wonderful talk. We'll have another talk same time on Thursday. That will be on representations of topological groups. So, thank you.